Hello everybody, welcome to today's video. Today is a continuation of our last video where we talked about the unit circle, mostly talked about sines and cosines using the unit circle, and a little bit of tangents, but today we're going to talk about the rest of the trig functions as well. So today's more on trigonometric functions. So we'll look at finding exact values for tangent, which we actually did a little bit before, but we'll also look at the cosecant, the secant, and the cotangent functions. So we'll kind of round out what we were looking at before with all of the trig functions here. We'll use reference angles to evaluate all 6 trig functions. We'll talk about which of the functions are even and which of them are odd, which can help us solve problems later on. We'll also talk about the periodicity, which I didn't write down here, but so we'll talk about the periods for each of the trig functions. And then we'll use some fundamental trig identities to simplify some expressions that can help us later on down the road. So first, I'm just going to remind you of the definitions of the trig functions and their domains. So we looked at the domains for the sine and the cosine last time, and we made some sense of that. So I'm just kind of stating those here, that the domain for the sine and cosine functions are just all real numbers. So there are no restrictions for those. The other ones are written in this very mathy notation, and so that's what this restriction column here is for, so that we can think about what's going on here. So for the tangent, that is defined as the y value, which is the sine, over the x value, which is the cosine, which means that there are some values which would not be good to plug in. If we plug something in that would cause the x value to be 0, then we would end up dividing by 0, and that would not be good. So let's think about what values would make the x 0. Like, when is x equal to 0? When is the cosine of t equal to 0? So this is what we are investigating. Well, I know that the cosine of 0 is equal to 1, so that's okay. But the cosine of pi over 2 is equal to 0. And it also happens to be that the cosine of 3 pi over 2 is equal to 0. And if we think about this, we could keep just traveling around more as well, right? So just maybe instead of just writing this down, I should, whoops, I'm trying to erase. I should just write what those points are, because I think that'll be a little bit clearer. So I know that this up here is the point 0, 1, and this down here is the point 0, negative 1, and each of those x values are 0, so we don't need to consider that one. But if we think about traveling around here, that gives us pi over 2. This gives us 3 pi over 2. This is going to give us 5 pi over 2. This gives us 7 pi over 2. This gives us 9 pi over 2. So as we spin around, it's just the odd multiples of pi over 2 that's doing that for us. So our restrictions here are the odd multiples of pi over 2. And that's what this very mathy notation over here is saying, that we are allowed to plug in any value of t so long as t doesn't equal, and if you look at this 2n plus 1 for all integers n, just think about plugging in any integer n. You'll always get an odd number. So if you plug in 1, you'd get 2 times 1 plus 1 is 3. If you plugged in 2, you'd have 2 times 2 plus 1 is 5. If you plugged in 3, you'd have 2 times 3 plus 1 is 7. So we get these odd multiples of pi over 2 here. And the same thing for the secant. If we plugged in any odd multiples of pi over 2, we would end up dividing by 0, and that's not what we want here. So same thing for the secant, that since the denominator is 0, we can't have any values of t that would give us either a cosine or an x value of 0. So that's why the tangent and the secant, which both have cosine or x in their denominators, we lose odd multiples of pi over 2 from their domain. So notice that there's infinitely many holes in the domain here. It's at every odd multiple of pi over 2. So let's think about now the other ones we have here. So let me erase my thinking from that one. But now we're looking at cosecant and cotangent. So let's think about when y is equal to 0, or when is the sine of t equal to 0, and this will be the spots that we want to throw out. So I think if we start over here, we've got the point 1, 0 that has a y value of 0, and over here we've got the point -1, 0, and both of those have y values of 0. Plainly stated there. So let's think about what angles do that for us. Well, 0 gives us that value for sine, and so does pi, and so does 3 pi, and so does 4 pi, and so does 5 pi. Oh, I'm saying those backwards. Let me try that again. We're starting with 0, and so does pi, and so does 2 pi, and so does 3 pi, and so does 4 pi, and so does 5 pi, etc. So as we're just spinning around the circle looking at angles, it's only the ones that hit at these points here, which are just the multiples of pi. So these are the multiples of pi. And same thing down here. Well, it's going to put y in the denominator. It's at every multiple of pi. So here are the restrictions on our domain, and that's what these very mathy notations are saying here, that we can plug in any value of t being our angle or our arc distance or arc length, depending on how we're thinking about that unit circle definition. But at any multiple of pi, so 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. We can't plug those values in and get an output for either cosecant or cotangent, because we would end up dividing by 0, and we can't do that. So here are the rest of the domains. We have sine and cosine. We can evaluate those anywhere. They have no restrictions on their domain. But the tangent and the cosecant means that we can't have these odd multiples of pi over 2, and the cosecant, I don't know if I said that right. The tangent and the secant means we can't have odd multiples of pi over 2, and the cosecant and the cotangent means we can't have multiples of just pi. So let's use all of these definitions now to get all the 6 trig functions at t corresponding to the point given here. So we've traveled this distance around. We're not exactly told what it is, but we could actually maybe figure it out by thinking backwards, but that's not what we want to do here. We just want to figure out what these values are. So we can see that we are living over here in the second quadrant. I want to get the sine, which is just the y value. So the sine, which is y, is just going to be the 1/2. And then the cosine is the other value, the x value, which is negative square root of, I should write that that's x, is the negative square root of 3 over 2. So we'll just use the relationships that we saw before to get the rest of the trig functions here. So tangent we know is y over x by definition. So we can write this as the y value is 1/2, and the x value is the negative square root of 3 over 2. I can multiply, oops, I don't want to multiply. I'll say this is equal to 1/2 multiplied by the reciprocal of the denominator, which is 2 over square root of 3. I'll just throw that negative wherever it kind of makes sense here. Just throwing it in the denominator for whatever reason. But then the 2's cancel here, and we've got negative 1 over the square root of 3, and then we can rationalize the denominator. Nothing wrong with negative 1 over square root of 3, but it is kind of nice to rationalize the denominator here, and we will get that this is negative square root of 3 over 3. So there we go. There is the tangent at this angle t, or this distance t out here, which we weren't given. We could say what it is, but that's okay. If we want to find the cosecant of t, this is going to be 1 over y, 1 over the sine value. So just plugging things in here, we have 1, sine is 1 over 2. If I then take a reciprocal, we are just going to have 2. So the sine value here, or the cosecant rather, is just 2, related to the sine. It's a reciprocal of the sine. The secant is going to be 1 over x. It is the reciprocal of the cosine function, and since cosine is just x, we get that the secant is 1 over x. So this is going to be 1 over negative square root of 3 over 2. And then we can just take a reciprocal there, and we will get negative 2 over the square root of 3. I can rationalize my denominator again, so nothing necessarily wrong with this answer, but it is nice to rationalize our denominators, and we'll have negative 2 square roots of 3 over 3. So there is our secant. And then for our cotangent, this is going to be x over y. That is how that is defined. So that's the cosine over the sine. So here we're going to have negative square root of 3 over 2 divided by 1/2. And we can multiply by the reciprocal of oops, I forgot my square root, negative square root of 3 over 2, and we'll multiply that by the reciprocal of the denominator, 2 over 1. Those cancel and we get just negative square root of 3. So there we go. We've got them all now. You can put boxes around the first two. We've got all 6 trig functions evaluated using this point here associated with t. All right, I just want to take a second and look at all of the common angles evaluated at all of the trig functions here, at least corresponding to that first quadrant. Is just kind of nice to see them all in one spot. And then we can use reference angles to just, use the quadrant that we're in to assign positive and negative values to all of these common values that we'll see here. So if we're thinking about starting with sine at all of the common values here, we're starting with an angle of 0. So just thinking about this angle here, this is the point 1, 0, which means that the sine value is just 0. That's the y value. And as we start to move up, when we get to 30 degrees or pi over 6, you can see that the sine value's increased some, right? It's moved up. In fact, it's moved up halfway already. Just going 30 degrees moves it halfway up. I'm going to leave myself a little bit of space there because there is a kind of a nice pattern to notice here as we go through this. And then as it moves to pi over 4, we know that this is the square root of 2 over 2. And as it moves a little bit more to pi over 3, we're going to get that this is the square root of 3. Write that a little bit better. Square root of 3 over 2. And then as it continues its trip all the way up to pi over 2, well, this is the point 0, 1, and so now it has reached a value of 1. So if we think about doing that same thing for the cosine, we might notice something exactly in reverse. So let me get rid of my thinking here, and let's see, we'll do cosine in green. So again, this point over here we're starting with is at 1, 0. So the cosine at this point at 0 is just equal to 1. And as we start moving along the unit circle here and we get to our first stop at pi over 3, we see that the cosine at that value is the square root of 3 over 2. So we're kind of moving in the backwards direction here. You might notice that pattern as we're going. As we get to the pi over 4 value here, this is the square root of 2 over 2. Maybe not too surprised to see that. We know that the sine and the cosine are the same at that spot. And then we keep traveling over to the pi over 3, and this is going to give us a cosine value of now just 1/2. So you can see that they're kind of swapping places here. And as we get to the very top here at 0, 1, we now have the cosine being equal to 0. So hopefully that's not too surprising, because we've seen before that these have this sort of relationship that as one goes up, the other goes down, and they kind of just flip-flop spaces here, especially if we think about the 30 degree and the 60 degree angles of the 1/2 and the square root of 3 over 2 and the square root of 3 over 2 and the 1/2. Just kind of swapping positions, and then the middle is the middle. Those are the same, and then the endpoints also being kind of flopped here as a way to think about this. I just want to notice some pattern here, because there is kind of this nice pattern of just increasing numerators. So I could write 0 as the square root of 0 over 2, and that is still just equal to 0. And I could write 1 over 2 as the square root of 1 over 2, and that's the same thing. Of course, the square root of 2 over 2 is just the square root of 2 over 2. And the square root of 3 is, of course, just the square root of 3 over 2. I keep forgetting to say the over 2 part, but it's the numerator that I'm focusing on. And then I could write 1 as the square root of 4 over 2. So you might notice, as if you're just focusing on the numerators, we've got square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. So there's just kind of this nice increasing square root going on in the numerator here, which is just a nice pattern to notice. It can help you kind of figure things out as you're working here. But just kind of pointing that out. It's not crucial to know that that is happening, but it can be a nice pattern to notice. So let's think about the rest of them here. The tangent is going to be I guess we can just stick with pink here. The tangent is going to be the sine over the cosine. So we've got 0 over 1, so maybe we're not too surprised to see that that is just 0 here. I'm just going to kind of fill these in. I'm not going to do too much of the thinking or algebra, but the idea here is we just want to get these values in. If I went through and I found the ratio of the sine to the cosine here, we would get the square root of 3 over 2. You can kind of see that happening. We've got a square root of 3 here. Square root of 3 over 3. Square root of 3 over 3. We end up rationalizing a denominator in that one. For the 45 for the pi over 4, we've got the square root of 2 over 2 over the square root of 2 over 2, which is just 1. So we've seen before that the tangent of 45 degrees is just 1. Here we're going to get just the square root of 3 for the tangent of 60 degrees, and then we will see that this is undefined because odd multiples of pi over 2 are not in the domain of the tangent. Let me go back and maybe remind you that for the tangent, we cannot have odd multiples of pi over 2, including pi over 2 itself. So that is why the tangent function is undefined at pi over 2. And we'll see as we start to graph these things that there is maybe more to the story going on here, but we're just kind of getting some of these important values kind of mapped in that we can use going forward. Okay, let's take a look at the cosecant, the secant, and the cotangent, and we're just going to be kind of looking at reciprocals here. If I want the cosecant, that is going to be 1 over the sine, which is 1 over 0. Uh-oh, we're undefined again. So undefined, we'll just put in the shorthand there, undef, because we would attempt to divide by 0 there. So, you know, again, we can reference back to our thing, our list here, that we can't have multiples of pi for our cosecant. So 0 is a multiple of pi. It is 0 times pi. So that is why we do not have this being defined for the cosecant. And then as we move forward here, we're going to take a look at the reciprocal of 1/2, which is just 2. We'll take a look at the reciprocal of square root of 2 over 2, which is just the square root of 2 if you rationalize the denominator. Taking a reciprocal of the sine here would give us 2 square roots of 3 over 3, and then we would get just 1. This reciprocal of 1 is just 1 at 90 degrees here. So there's the cosecant. If we want to get the secant in here, it should just be the reverse order of the cosecant. So just like sine and cosine have this kind of reverse pattern here, it'll be the same thing for the cosecant and the secant. So we'll start with 1, and then we'll have 2 square roots of 3 over 3, and then we'll have the square root of 2. Hopefully we're not surprised that at 45 degrees we get the same value. Over here we will just get 2, and then we will have undefined for our odd multiple of pi over 2 there. And then for the cotangent, we should just get the opposite listing of the tangent. So over here, we cannot have 0 in the denominator, which means that we can't have sine in the denominator here. This is x over y. So this one's going to be undefined. And we'll just shorthand that one there as well. And then we would have the square root of 3 here. We'd have 1. We'd have the square root of 3 over 3. And then we'd have 0 down here. So here is the full table kind of filled in at all of these common values. I think knowing the sine and the cosine and the tangent are usually enough to get through a lot of stuff. You can figure out the cosecant, secant, and cotangent by just looking at reciprocals, but you're going to see these values so much over the next few semesters that some of these things are just going to get beaten into your head as you work through stuff. But here you have them kind of all spelled out for you. I'm going to get rid of these blue ones here just so if you wanted to take a look at this full thing, not being so cluttered, there is our full list of all these values here. So now we are going to use reference angles to find all 6 trig functions, and we can use some of those values that we saw on the previous page in order to get some things sketched in here. So we want to look at negative 5 pi over 6, so we don't know exactly what that point is, but we should be able to figure that out using reference angles here. So here theta is equal to negative 5 pi over 6. What we are looking for is theta prime which is this distance right here. So theta prime. And hopefully you could be convinced that we would need to go one more pi over 6 in order to get to that horizontal axis there. So here our reference angle is going to be pi over 6. So let's just use things that we know about pi over 6. We know that the cosine of pi over 6 is equal to the square root of 3 over 2. And we know that the sine of pi over 6 is equal to 1/2. Since we are in quadrant 3, we know that the cosine of whatever is going to be negative, and the sine of whatever angle is going to be negative. So now we know that the sine is going to be negative 1/2, and the cosine is going to be negative square roots of 3 over 2. So we could even list those in over here if we wanted. This is negative square root of 3 over 2 and negative 1/2. So there's the point that we're at. And now we'll just use these relationships to get the rest of the trig functions here. So tangent is going to be y over x. So remember that sine is y, cosine is x. So y over x is going to be negative 1/2 over negative square root of 3 over 2. This is going to give me negative 1/2 times negative 2 over the square root of 3. The 2's cancel, the negatives cancel. I get 1 over the square root of 3, and if we rationalize the denominator, we'll have the square root of 3 over 3. So again, either one of those work for me. Not super vigilant about rationalizing denominators, but I usually do if given the chance. So there's our tangent, which probably we're not super surprised to see. If we're looking at the tangent of pi over 6, we would see that the tangent at pi over 6 is the square root of 3 over 3. We know that the tangent is always positive in the third quadrant, so we're not too surprised to see that we get positive square root of 3 over 3 here. So we can just straight up use those values to compute these. So if I just want to find the cosecant of t, let me just reference back here. Our reference angle is pi over 6, so we're going to be looking in general. Let me maybe put those back on there. In general, what color do I want? We'll do blue. At this box here. So this is where we can focus to get a lot of these values here, and so we can just reference back. So again, if I'm looking for cosecant of t, cosecant is 2. So we can get a 2 in here without having to do any work, and now I just need to remember which functions are positive and negative in this third quadrant. So they are all positive here. Maybe I should have started with this. Maybe I'll do this in a different color. But all trig functions are positive here. So we have a smart trig class. Here we would have that just the sine is positive, but that would tell us that the cosecant, and I'll just abbreviate, sine and cosecant, are both positive here. All positive. These are the positive ones here. Here, tangent and cotangent are going to be the positive ones. And here, cosine and secant will be the positive ones. So now that we've got those in here, cosecant is 2 at pi over 6. And since we're in the third quadrant, where only tangent and cotangent are positive, this tells us that this will be negative 2. So just using that common value, cosecant of pi over 6 is 2. Since we're in the third quadrant, we know that it's going to be negative 2. And we can do the same thing here for the secant of t. So if I look back to our list here, the secant is going to be 2 square roots of 3 over 3. So if we look back here, I know this is going to be 2 square roots of 3 over 3. And then I just need to get the sign right. Since the secant is negative here, we need to put a negative in front of it, and there we go. So without needing to do too much work, we'll get the value that we need here. And then cotangent, if we go back and look at our list, cotangent is square root of 3. So we know that this will be at least the square root of 3. And since cotangent is positive in the third quadrant, we know that this is positive as well, and we can just leave it alone. So there we go. We are just using a reference angle. We are using the values that we found before. We are using the quadrant that we're living in to kind of somewhat get us a shortcut to what we want here. So next we're going to talk about which of the trig functions are even and which of them are odd, which can have some important consequences going forward, especially when we start thinking about trig identities and trying to combine addition, subtraction, multiplication, and division of different trig functions in order to just condense them down as far as we can to get something nicer. So just a reminder of the definitions here. If we have an even function, it says if you plug in negative x, so f of negative x, you just get f of x back. So plugging in a negative version of the input should give you the same output. And then the definition for odd means if you take your input and you make it negative, then the output becomes negative. So if you do f of negative x, then you get negative f of x. And there's some geometric consequences or relationships there that we will continue to notice as we go forward. So let me just get rid of my chicken scratch here. And we'll start thinking about each of these functions here. So here, the input here isn't an x value or a y value or something, but it's t. So we're inputting some angle, or we're corresponding the angle, since we're thinking about a unit circle here, to this arc length distance here. So if we're going to plug in, let's say, or let me put some values on here. So if we're going to move t, then this would give us the point xy. So this point here is the point xy. But if we move back in the negative t direction, well, you can see that the x values are still going to be the same. We're still going to have x, but y has now become negative. So we have negative y here. The values will still be the same. The absolute value will still be the same. It's just the sign that's changed from positive to negative here. So if I'm thinking about, let's start with cosine. If I'm starting with, we'll keep yellow, cosine, let me scoot that over a tiny bit. Cosine of x, I'm sorry, of t, we're plugging in t. Cosine of t is equal to x. So that's this guy right here. And if I look at cosine of negative t, well, that's also just x. So here what we see is that the cosine of negative t is equal to the cosine of t, which tells me that cosine is even. And so we will throw in its counterpart here, the secant, just its reciprocal, that the secant of negative t is also equal to the secant of t. So we know that these two now are even. Cosine and secant are even functions. Let's take a look at this other side here. I haven't left myself a ton of space. Maybe I can scoot this over a little bit. Kind of works. Missed a couple little guys here, but that's okay. All right, let's take a look at the odd side here. And of course, I know what's coming here, so I know where to put them. But if I wanted to look at the sine of t, that just gives me y. So I'm talking about this guy right here, just the sine of t. If I take a look at the sine of negative t, what I end up getting here is negative y. Negative y. Since sine is equal to y, if I get negative y, then that's the same as negative sine. So here we get that the sine of negative t is equal to the negative sine of t, which tells us that sine must be odd. So we're going to throw in its counterpart as well. The cosecant of negative t is also equal to the negative cosecant of t, since it's just a reciprocal of sine. So here we've got the odd boys. Trying to close that box off, but here are our some odd functions. So cosine, secant, even, sine, cosecant, odd. So the other two that we need to investigate here are, of course, tangent and cotangent. So let's think about tangent. The tangent of t is going to be the y value over the x value. The tangent of negative t is going to be negative y over x. Negative y over x, which is equal to negative y over x, which is equal to the negative tangent of t. So here we see, similarly, we get that tangent of negative t is equal to the negative tangent of t, which means that tangent is odd. So we will throw in its counterpart here. Its reciprocal, cotangent of negative t, we would see would give us negative cotangent of t. So a couple more odd boys here. So there they all are listed out. The only ones that are even, oh, I'm missing some of my symbols here. The only ones that are even are cosine and secant, and all of the rest are odd. Sine, cosecant, tangent, and cotangent are all odd functions. So we can use this going forward, thinking about some of our trig identities in order to simplify. Here's just a list of some fundamental trig identities. We're going to use this, like I said, to try and simplify some expressions going forward. We'll see some examples in a second. But most everything on here, 1, 2, 3, 4, 5, 6, 7 of the 9 that are on here, we should already know. So this guy here is just the definition of tangent as being y over x, so we could see that this is the same as y over x, and we know that y is equal to the sine and x is equal to the cosine, so we can just use this relationship that tangent of t is equal to the sine of t over cosine of t, and then we can just use that reciprocal property, or just the fact that cotangent is defined to be x over y, to get that the cotangent of t is the same as cosine t over sine t. So we can always make these substitutions. That's the idea with these identities here, is we can always make these substitutions in order to simplify. Then we have all the reciprocal identities. So, of course, tangent is equal to the reciprocal of cotangent and vice versa. And then secant is equal to the reciprocal of cosine, and cosecant is equal to the reciprocal of sine. So just things that we had already seen before. So these first 1, 2, 3, 4, 5, 6, we all get for free. And then the 7th one here, we also know from seeing before that this is just the Pythagorean theorem. This says that x squared plus y squared is equal to 1. The 1 is the hypotenuse, so we have the legs of a right triangle being squared and added together is equal to the square of the hypotenuse. So the only two that we haven't seen like a reason for, the other two that are listed here. So let's just quickly go through and show that these are what I say that they are. So what we're going to do is take the Pythagorean identity that we already know, and I'm going to divide every piece here by the cosine squared of t. So I'm just dividing both sides by the cosine squared of t. So there's the left-hand side, and now the right-hand side, the cosine, let me write that better, the cosine squared of t. Now if we simplify each portion of this here, cosine squared of t over cosine squared of t just gives us 1. And if we look at the sine squared of t over the cosine squared of t, well, sine over cosine is tangent, so if you square them, then you get the tangent squared of t. We could work that out a little bit more rigorously, but you can trust me that works out. And then we've got 1 over the cosine squared t, which is just the secant squared t. So we are just dividing both sides by cosine squared t, and we are getting this new relationship here of 1 plus the tangent squared t is equal to the secant squared t. So whenever you see one or the other of those expressions, either 1 plus tangent squared or secant squared of t, you can always just substitute in the other one. And then lastly, if I to get the final one here, if I divide both sides not by cosine squared t, but by sine squared t, sine squared t, sine squared t, then we would see in the first slot here, this is just the cotangent squared t. Sine squared over sine squared should just give us 1. And that is 1. And then 1 over the sine squared is the cosecant squared, and there's the cosecant squared. So we are just getting these other two Pythagorean identities from the first one. We're just dividing both sides by the same function being squared, and we get these results here. So let's put these all together here. Now that we've got all these trig identities, and we will continue to develop more of these as we go. But let's look at a couple of examples here. So the first two are pretty straightforward. The last one is a bit more intense, but that's going to be more of what you see in the homework. So here I'm just going to rewrite things the way that I know them. Secant t, well, I can use the reciprocal identity here. That's going to be the same as cosine t. And then the tangent of t I can write as sine t over cosine t. All right, well, now I can just do some algebra. This says 1 over the cosine of t times the cosine of t over the sine of t. Well, now those cosines of t cancel, and we're left with 1 over the sine of t, which is the cosecant of t. So there we go. We have simplified this ratio, or this division, this quotient of some trig functions down into a single trig function with no more fractions left over. So let's take a look at this next one here. I think that this one actually goes pretty quickly. We've got tangent of t, which I could rewrite as sine of t over the cosine of t, and we're multiplying this by the cosine of t. So I could always just put that guy over 1. Those cosines of t cancel. We're left with sine of t over 1, which is just the sine of t. So there we go. Like I kind of saw coming. That one works out pretty quickly here. This last one's going to take a little bit more effort, and we're going to put a lot of things together here. So the first thing I'm going to use is the evenness and oddness of these functions here. So I know that since the cosine is even, that the cosine of negative x is the same as the cosine of x. I know since tangent is odd, that the tangent of negative x is the same as the negative tangent of x. So there I'm putting the negative on the outside. And I also know that the sine of negative x is the same as the negative sine of x. So here I'm kind of thinking about, I don't want to say pulling the negatives out, but you can kind of think of it that way when you have odd functions. So this is just using the fact that cosine is even and that tangent and sine are odd to make this first step here. Now I'm going to use these relationships that I already know. Cosine, of course, is still just cosine, so there's that. And now on my denominator, I'm going to rewrite negative tangent x as negative sine x over cosine x. And we are still subtracting sine of x. Okay, now I'm going to multiply by the reciprocal of the denominator in this first half of the expression here. So now we're going to have cosine x, and we'll just put this over 1, being multiplied by negative, maybe I'll just put this negative in the very front, negative cosine x over sine x. And we are still subtracting sine x. So now I can multiply, let me just put a little visual separator here. Now I can multiply the left-hand side together, and I'll have negative cosine squared x over sine of x minus sine of x. Since I'm trying to get this into a single trig function, I think now I need to do the subtraction. So let me get a common denominator here. I'm going to throw in my funky form of 1, and that looks like sine x over sine x. So notice that everything I just wrote in purple there is all just 1. And I'm doing that so I can get a common denominator. So now in my next step here, I should have the negative cosine squared x minus the sine squared of x all over the sine of x. Now in the numerator, I can factor out a negative, and I'll have negative cosine squared x. I'll just put in another visual separator here. Negative cosine squared x plus sine squared x all over sine x. Now we'll use one of our Pythagorean identities that says that if you have cosine squared of whatever plus sine squared of whatever, then that just gives us 1. So going in and putting the rest of what we have here, there's still a negative. This is still over the sine of x, but this tells us that we've got the negative cosecant of x, squeezing it in there at the very end. We've got the negative cosecant of x. So there we go. That one took a lot more work, a lot more identities to get there, but we got it down to a single trig identity. Maybe I scoot this over a little bit. Oops. And maybe I write the answer a little bit cleaner, but we've got it now, negative cosecant of x. All right, I think the last thing that we want to do here is talk about the period of a function, and this will lead us into trig functions, of course. But the period p of a repeating function f is the smallest number such that f of x plus p is equal to f of x for any value of x. So not just some of the values of x, but for every value of x. So I've got written down here that the period for sine, cosine, cosecant, and secant is 2 pi. So let's take a look at why that might be true here first. We're going to start, let's maybe start with cosine. So I'm going to, whoops, watch going off here. We're going to start with cosine. So if I think about the cosine at 0, that is equal to 1. So this is the point 1, 0 here. The cosine of 0 is equal to 1. So let's think about when the cosine would be 1 again. So as we start moving our angle around, cosine is down to 0. Well, now cosine is down to -1. Now it's starting to turn back around, and now it's back to 0. So we see a repeating point here. We've seen 0 show up twice at a value of just moving pi radians around, but we haven't gotten 1 again, which means that even though pi is showing up for 0, it's not showing up for 1. But if we get all the way back around and we travel a distance of 2 pi, then we get that the cosine is 1 again. So we see that the cosine of 0 plus 2 pi is also equal to 1. So here the period p must be 2 pi. So that's not exactly a proof, but it is showing, at least for this one value, this one output value, that 2 pi is what we needed to get all the way to the same value that we started with. We can do the same thing with sine. We can think about sine of pi over 2. That is equal to 1. So I'm always thinking about where things are equal to 1 and then seeing where we get back to 1 again, because 0 can happen at spots less than the period, if that makes sense. So over here, we've got the point 0, 1. So when does the sine become 1 again? Well, we start to travel down. Now the sine is 0. And we keep traveling down. Now the sine is -1. And we keep traveling up. Now we're back to 0, but we don't hit 1 again until we get 2 pi traveled all the way around. So here we don't see 1 again until we do another revolution of 2 pi, and then we get 1 again. So again, here the period is going to be 2 pi. I guess I should maybe box the first one too. Okay, so there's cosine and sine, and with those come along cosecant and secant. They have the same period, and I'm just going to kind of lump those in, and we can think about that more as we look at the graphs of these later on. Now I want to take a look at tangent. So we're going to think about when tangent is equal to 1, and tangent is equal to 1 at pi over 4. Because this is where we're going to have square root of 2 over 2 and square root of 2 over 2. If we look at the ratio of those, we just get 1. So it is the tangent of pi over 4 that gives us 1. So now we want to think, okay, when are we going to get a tangent value of 1 again? What angle will give that to us? And as we start traveling around, this one's harder to see since the tangent is the ratio of two functions here. So I'll just maybe spoil the surprise, and we'll see that once we get back down over here, this is negative square root of 2 over 2 and negative square root of 2 over 2. And if you take the ratio of those, you get 1 again. So this is at an angle, well, we've moved pi all the way around. My line didn't end up being exactly straight, but that is 180 degrees that we've got to get there, or a value of pi. So tangent of pi over 4 plus pi gives us 1. So here the period for the tangent function is just pi. And same thing with the cotangent. So there's a little kind of brief explanation for why we get the periods the way we do for these, and we will use these more going forward as we start looking at the graphs of these functions. So for there, it looks like it's time to practice, so I will leave you to it. Good luck with your work. If you have any questions, please let me know. I'll see you in the next one.